Hey everyone, and welcome to this explainer. I am absolutely thrilled to take you on a journey today into the hidden, underlying logic of how software seamlessly reacts to our everyday inputs. If you're someone who loves to understand the invisible structures that make our modern digital world function, you are in the exact right place. We're going to unpack the fascinating evolution of event-driven programming.
So let's start here. How does a piece of software actually know you just clicked a button or swiped a screen? It feels totally instantaneous to us, right? We tap and boom, the app responds. But beneath that simple interaction is a complex architectural triumph that's literally been evolving for decades. To truly grasp how our devices come alive, we really need to answer this fundamental question about how event-driven programming works. To get to the bottom of that, here is our roadmap for today. 1. The heart of dynamic systems. 2. The handler's design pattern. 3. Events in the real world. 4. Solving the observer problem. And finally, 5. Advanced event architectures. All right, let's jump straight into part 1, the heart of dynamic systems, focusing on state machines and events. Okay, let's dive into this by exploring how the dynamic aspects of systems are modeled before a single line of code is even written. Think about a common recycling machine at your local grocery store. Before you walk up to it, the software is just sitting in an idle state, waiting. When you insert a bottle, an event is triggered. That event forces the machine to transition into a process item state, where it classifies what you just dropped in. When you hit a button to finish, another event fires, transitioning the machine into a print receipt state. The vital takeaway here is that events are the absolute key to understanding these state machines. They're the catalysts. They force a system to move from one state to another. Without events, the software is literally just frozen in time. Moving right along to Section 2, the handler's design pattern, tracing it from 1975 to today. We're going to trace this logic back to its historical roots to see how developers first wrestled with this concept. The 1975 Transaction Analysis Data Flow Graph by Jordan and Constantine might look a bit like a tangled web from a vintage textbook, but honestly, this is widely considered the ultimate archetype of event-driven programming. It introduced this brilliant concept of a central hub, which they called the transaction center, that takes in an incoming stream of data and splits it into specific outgoing substreams based entirely on what just happened. To make sense of that dense 1975 logic, we can break down the job of that transaction center into 4 really digestible steps. First, it has to get the transaction, or the event, in its raw form. Second, it has to analyze that transaction to figure out exactly what type it is. Third, it dispatches it based on that specific type. And fourth, it relies on another part of the system to actually complete the processing. And those 4 steps perfectly illustrate how things evolved into Stephen Ferg's famous handler's pattern. In this setup, you have a dispatcher that acts exactly like a traffic cop. It uses something called an event loop to constantly grab incoming events, figure out what the heck they are, and route them to the appropriate handler. The handler is just the specific block of code that actually does the real work, like opening a menu or saving your file. Now, let's see how this builds into what's known as the extended handler's pattern. Sometimes you don't actually have a human clicking a mouse. Sometimes the software itself needs to generate the events. We see this all the time in simulation software, like traffic simulators, or when you use a click method in JavaScript to programmatically simulate a user's action. In this case, an events generator feeds the dispatcher, which then feeds the handlers. But architecture is super flexible. In what's called a headless variant, the dispatcher is actually entirely removed. We're just left with a direct collection of handlers. This is really typical in publish and subscribe systems. The events go straight to the handlers that are subscribed to them, which completely streamlines the process when you just don't need a centralized traffic cop. Which brings us to Section 3, Events in the Real World, Interfaces and Sensors. So, we've looked at the abstract flowcharts, but how do these patterns actually manifest in the physical devices you and I use every single day? Well, just think about graphical user interface, or GUI, events. Buttons, checkboxes, text boxes, mouse clicks, keyboard presses with Shift or Alt modifiers. GUIs are absolutely overflowing with events. What you really should take away from this is the sheer scale of the programmer's job. Using frameworks like Java's Abstract Window Toolkit, a developer has to write specific handler code for every single significant action a user might possibly generate. Because if they don't write a handler for a specific button and you click it, absolutely nothing happens. And it extends way beyond just our screens into embedded systems. Our real world is completely full of sensors picking up everything around us.
Thermostats detecting temperature, automatic doors sensing proximity, cameras acting as visual sensors, even industrial alarms detecting gases. Every single one of these physical changes is captured, translated into a digital signal, and handled as a software event using the exact same handler patterns we just talked about. So, here's a crucial question. What happens when all these sensors, or let's be honest, impatient users, generate events too quickly? Imagine wildly shaking your mouse while frantically clicking. You can easily overwhelm the software. That's exactly why systems use an event queue. It's basically a buffer placed right before the dispatcher. If events arrive way faster than the handlers can process them, the queue holds them in line. In fact, in many GUI applications, just to keep the system from totally crashing, the queue is actually programmed to simply discard accumulated events, like those frantic, useless mouse movements, just to empty the buffer. Naturally, as the volume of events grew over time, the nature of the event itself had to evolve. In early, pre-object-oriented languages, an event was often just a simple string of text or a basic transaction code. It essentially just said, click. But today, in modern object-oriented programming, events are complex objects. When you click, that event object carries rich, detailed data with it, like the exact screen coordinates of your mouse, the exact millisecond it happened, and the specific UI element that triggered it. It gives the handler so much more context to work with. All right, let's move into section 4, solving the observer problem through notification systems. As software got more and more complex, a fascinating challenge popped up. How does one isolated piece of software know that something absolutely crucial just happened in a completely different piece of software? We call this the observer problem, and I guarantee you encounter it constantly. In stock trading, the buyer software needs to observe fluctuating prices. On social media, the notification system has to observe when your friend posts a new status update. In game development, the on-screen GUI health bar needs to constantly observe the underlying player mechanics so it knows when your health drops. The subject is where the action happens, and the observer needs to react to it. Now, historically, observers would just constantly pester the subject, asking, "Did you change? Did you change? Did you change?" As you can imagine, this caused massive processing overhead. So the elegant, common-sense solution to this is what developers affectionately call the Hollywood principle. Don't call us, we'll call you. And here is how the Hollywood principle actually plays out in code, which is formally known as the observer pattern. Instead of the observer constantly checking for updates and wasting tons of system resources, it just registers its address with the subject. It basically says, "Hey, here's my card. Let me know if anything happens." The subject then maintains a list of all these registered observers. Then, and only then, when an interesting event actually occurs, the subject pushes a notification out to everyone on its list. It is an incredibly efficient way to handle things. And finally, Section 5, Advanced Event Architectures, where we'll look at some core philosophies and applications. To really appreciate the philosophical implications of these patterns, we have to look at a deeply fascinating controversy among computer scientists. In early programming, the go-to statement was heavily criticized because it made code jump around unpredictably, which made it nearly impossible to follow. Well, some theorists argue that implementing the observer pattern is fundamentally like creating a come-from statement. Because handlers are literally just waiting for a dispatcher to trigger them from afar, a programmer reading a handler's code might have absolutely no idea where the trigger is actually coming from. It makes modern interactive code incredibly powerful, for sure, but also somewhat mysterious to trace. And this idea is taken to its absolute extreme in modern paradigms like aspect-oriented programming, or AOP. In AOP, the observer pattern is structurally baked right into the code at a fundamental level. You don't even have to manually write the registration list or the dispatcher logic anymore. The language itself inherently observes state changes, like a point changing its X and Y coordinates, and automatically updates connected displays. The event reaction becomes less of a manual instruction and more like a law of the software's physics. Which brings us to a final, pretty provocative thought. We've spent this explainer seeing how software has spent half a century evolving these incredible patterns, dispatchers, queues, observers, all just to perfectly capture and react to our inputs. But as you use your smartphone today, consider this. If our software is so perfectly structured and optimized to react to our every single move, are we truly driving the system, or is the system quietly training us to be the perfect event generators? Think about that the next time you feel completely compelled to click a notification. Thank you so much for joining me on this explainer. Keep learning, and I'll catch you next time.